Okay. So basically last class I think we did two community structure identification algorithms. One was the spectral bisection and another was that Uberman algorithm, where you used we thought the graph as a network of current and voltages of resistance, okay, and we showed that we can essentially bisect based upon some thresholds. Okay. So, I go forward with another set of community structure identification algorithms, and the idea is, so what is happening is you have a community, and if you are thinking that this is the community edge, somehow the concept is there is these two nodes are dissimilar or these two nodes belong to different communities. So, the similarity index is low. Okay. So, that is how you somehow differentiate or somehow divide nodes, but you can think it in another way, that when is this edge a community dividing edge, when is this edge a community dividing edge? When it has high betweenness. Okay. If it has high betweenness, that means a lot of messages passing through this, lot of messages passing through this, which means it acts as a bridge between two communities. Okay. So, it is actually acting as a bridge between two communities. Acting as a bridge between two communities. So, what will be the general form of the algorithm? 1. Calculate betweenness, scores for all edges, okay. So, this is a little different from so what we studied is, we have just mentioned that there is something called edge betweenness, but when we previously talked about betweenness centrality, it was upon nodes. The betweenness centrality was upon node, but uh, what are we doing here? We are actually calculating the betweenness of edges. Okay. So, this is little different from betweenness centrality, just keep this in mind. Okay. Then find the edge with highest core, okay, and remove it. Okay, from the network. Then recalculate and repeat step 2. Yeah, we need to recalculate. We need to recalculate, because once one node is removed, for example, if one edge is removed, basically the betweenness will change. The edge betweenness will change. For example, I am giving you a trivial case. Okay. Take this example. Now, when I remove this edge, when I remove this edge, okay, betweenness of this will change.
But we are interested in the overall community as such. So we should be interested in the one basic snapshot of the betweenness, not recalculation.
No, actually what is happening is we are continuously going on building communities. So
the community will remain the same.
No, community will not remain the same. So, you see what can happen is, if I remove one edge, then what are the possibilities? The one possibility is it is getting disintegrated, okay, getting disintegrated. What is the other possibility? That actually shortest paths get increased, shortest paths get increased. So, now think some edges were on the path of the shortest path in the previous case, now they are not, because you have to take an alternative route. So, you can think that there is some path out here with this. Immediately what is happening? Once this node is removed, the edge bit, there is one path out here. Okay. So, immediately when we remove this, the edge betweenness of this changes. Okay. How are this shortest path? Yeah, because this, see, there may be a route from here to here, say of 1, 2, 1, 2, 3, 4, 5. So, this path, let us say this is path 2 is 5, while path 1 is 3. So, what is happening now? Since path 1 has got disintegrated, because you have removed this edge, there is no path 1. So, path 2 has become the shortest path now. So, this is, how is it same? It was path 3 previously, now it is 5. The shortest path length was 3 previously, now it is become 5 now. Okay, length is increasing. So, the question is, means I think it was covered in the previous classes that when I remove edge, there can be two effects. One is the entire network gets disintegrated, or shortest paths. Some shortest paths may increase, may not also increase, because there may be redundancy. So, there may be another path of just length 3. So, even if you remove this edge, the shortest path does not increase, but ultimately shortest path will increase. If you go on removing edges, either what you are doing, at least you are removing redundancy. Okay. So, I hope this algorithm is clear. Okay. So, now the questions which we can ask is, what is betweenness? Okay. So, the question which we can ask is, what is betweenness? So, betweenness can be shortest path betweenness, yeah, we can repeat that till graph gets disconnected, or we can repeat that up till some desirable configuration comes. So, it is a very important question, that how long to repeat is as long as the graph gets totally, every one extreme step can be that everything gets single, every node becomes single, that is one. Another is, perhaps we know some desirable configuration. So, up till that desirable configuration. Yeah, means it may be number of communities, it may be the structure of the community. You can have some algorithms where you say, no, I need 3 communities. So, accordingly stop it, or you can say that I need good communities. I do not know what is the definition of good, we will come to it, but we can say these things. Okay. As long as I am getting good communities, I go on, no point in doing it further. Okay.
So what are the communities here? And like after the first iteration, suppose they are asked what are the communities after the first iteration?
Yeah. So the point is, see, community identification after first iteration, let us say we have 2 pair of the network has disintegrated into 2 parts. Let us think. Okay. Now, what we have to see, is this disintegration good or bad? Good or bad means what I am telling, that you can see heuristically that say you are doing some community identification of this class, and you do some H calculation and you see BTEX, MTEX and duals are forming 3 communities. Perhaps that is good or that is intuitive, but
What are the 2 parts here?
what are the
What are the 2 parts? What 2 parts is it being?
no, we do not know what are the 2 parts. We have a network of students.
No, if we remove one edge,
Yeah.
how do we get 2 parts? We still have a graph.
No, we told that if we remove one edge, that necessarily does not give you 2 graphs. If you remove one edge, 2 impacts can happen. It can give you 2 graphs, or it is slowly removing redundancy, and ultimately if you go on doing this iteratively, you will get 2 graphs. Not removing the first edge will give you 2 graphs.
So whenever we get 2 disconnected components,
Yeah. Whenever we get 2 graphs, then we say that a community is formed, and then we can go on doing it, or we can say no, this is good or bad, or we can abort it. So, what you remember, that all these community identification algorithms are it is a application specific. So, it works good for some data, it does not work good for other data. So, it may so happen that you may continuously begin to get community of this type. Okay, if you go on doing, you may get community of this types. Okay, and like if you try to specify, no, that community 1 will have n1 nodes and community 2 will have n2 nodes, then it will be continuously like this, when same size, which is also not natural. Okay. So, what we can say is that every community identification problem suffers from this inherent problem. Therefore, one important area of research is that given a community, given a community set, can we objectively tell whether this is a good set or a bad set, not looking at the data even. Okay. So, if we look at the data, we can make many inferences, like if I try to run community identification algorithms on phonemes or on alphabets, and if we see that vowels are going in one direction and consonants are going in another direction, just by looking at the data we can tell something. But what I want to say, that I do not know what the data is, I just know the relationships, then can I devise a metric so that I can say, okay, this has been a good community. Okay. This has been fairly modular. We will come to that and we will define that. But first let me go to this question, that what is shortest path betweenness. Okay. So, betweenness can be shortest path betweenness, means how many edges pass, how many shortest path encompass this edge, how many shortest path encompass this edge. Okay. And second can be random path betweenness. So, what is random path betweenness? If I take any node S and any node T, and I let random walkers move, Okay, and here is the edge uv, here is the edge uv. Okay, here is the edge uv. How many times this random walker has passed through this edge, which will be typically uv minus number of times uv minus number of times vu. Okay, means a random walker will continuously go like this. So, we ignore that and we think in one direction, that how many times it has. Yeah, we take any pair and say that if there was a random walker which has gone for infinite number of times, can we find the asymptotic limit, so that we can say that it has passed through uv t number of times. And how do we find it? How many times it has passed from u to v minus how many times it has passed from v to e. Okay. We will come to the details, but this is the concept. Let us believe the concept and go forward. Okay. So, now what is shortest path?
So we say T is the betweenness.
Yeah, T is the random betweenness, random path betweenness of this edge. Okay. The minus comes because see, this is again convention, you may as well ignore it, but the path point is that one is passing from u to v and again coming back from v to u. So, in a random motion, in a random walk, there will be always a case where this persons will go on infinitely. Okay. So, you want to avoid those loops. So, that is why you try to take one direction.
So what is TUV?
Number of times the random walker has passed from u to v, and number of times TUV is number of times a walker has passed from u to v, while TVU is a walker passing from v to u number of times, when given a source and a destination pair. Okay. Which are fixed, and then summing it over all such pairs. Okay. Given a source destination pair and summing it over all such pairs.
So, to calculate random path betweenness, we will first take a set of random walks.
We will come to the algorithm, do not worry. Okay. So, this random path betweenness may look very odd, but once we do the calculations, we will see that there are easy ways to really estimate that. Okay. So, first let us do shortest path betweenness. So, what is the time take given a pair, what will be the time taken to calculate the shortest path? It will be m. So, you run a BFS, so it has to traverse all the edges. So, given a pair, it will be order m. Okay, you have to run a BFS and that BFS will traverse all the edge. So, the complexity is bound by the number of edge. So, there are n square pairs. So, the total complexity will be order m n square. Okay. Then for sparse graph, what is this? What in sparse graph, what happens? Sparse graph, it becomes order n cube. In sparse graph, the property is m. Okay. So, it becomes order n cube.
Even if it's a dense graph, you have to find out shortest path between
Yeah, so this is the naive algorithm which we say. Now we try to develop an algorithm and try to compute it in order mn. Okay. So algorithm to calculate in order mn. Okay. So what happens is the simple point. So you build up a BFS. So the BFS can be a tree. The BFS can be a tree, or the BFS can be a BFS forest or BFS graph, or I will just tell graph, okay, for or acyclic trees or acyclic graph, something like that I want to say. Okay. So BFS graph, let me. So now if it is a BFS tree, say I take this example. Okay, this is source and I build up a BFS tree. So now can we see that how many shortest path passes from this edge? How many shortest path passes through this edge? 1. How many shortest path passes through this edge? 2. Through this 1. Through this 4. So 1, 2. So simply if I have, if what is the algorithm then? Identify the leaves, assign 1 to all the edges connecting the leaf
rest of the n node, shortest path from any leaf node, which rest of the n minus 1 node will have n minus 1 shortest path. So it should have n minus 1.
No, we come. This is I am taking a single pair. I am taking a single pair. So then 3 is assign 1 to all the edges and go up and add 1 plus Wi, where Wi is weight of the dotted edge, summation of okay. So you just sum and there is the dotted edges. 1 plus Wi, where 1 plus summation Wi, where summation Wi is the weights of the dotted edges. Okay, is the summation of the weights of the dotted edges. Okay. Yeah, we are assuming there is no cycle. So if it's a tree, we have assumed that there is no cycle. So if it's a tree, then it's very simple. So this then is a order m algorithm, because BFS has to be run, that is order m, and traversing up is also you are just traversing according to the number of edges. So that is also order m. So the entire thing finishes order m, and then you have to do for all set of S. How many S are there? N. Each node, for each node you have to do that, and then you get it. I hope it's clear. Okay. So now let us take a more general case where you get a graph. Okay. So, this is the graph given. So, now how to identify? So, what you can do, first you can level the nodes, means the depth of the nodes. Okay. So, this is one. This you can say 0. This is the first level. This is the second level and this is the third level. Okay. So, you know the labels. Now, you want to identify, since this is a forest or a graph sort of thing, that means there are multiple shortest path passing. So, now I want to identify how many shortest path pass through each node. Okay. So, then that would be that this initially, so this has 1, this 2 has 1. Okay. Now, what you see, okay. So, take this and come here, this will become 1, take this node and come here. So, one more shortest path. Okay. Now, come here, so there is one more shortest path. So, this will become 2, this becomes 1. Okay. And this will become, for here it will become 2, and from this it will become 2 plus 1, 3, and here it becomes 1. Okay. So, first step is clear, that you identify the labels. Okay. You identify the labels. So, now I try to give weights, assign weights. Okay. So, what happens is, initial vertex, okay, initial vertex WS is equal to 1, no problem. Okay. Every vertex adjacent to S will have WS, W is equal to 1. Okay. So, now for I in level x, say, okay. So, x is equal to 1, I say, I start with the first level, x is equal to 1. For I is in level x, what happens? If j adjacent to I, if j is adjacent to I, and if j is adjacent to I, and what? Tell me. And j has not been assigned any weight. If j is adjacent to I and j has not been assigned any weight, like for this case again I say I is this one. So, initially j is this one, okay. nothing has been assigned to j. So, assign how much? Assign j is equal to weight j is equal to weight I. Okay. Whatever is the weight of I, that will be the weight of j. No problem. Now, think of this. Now, we come to this node. Here, when we see j has been already assigned, if j has been assigned, j is already assigned. So, then what is the condition we have to check? If j is assigned, what can be j? See, think j can be this one, j could have also been this one. I think from this node, j could have also been this one and j could have been this one. So, what are the possible levels of j? What can be a possible level of j? No, it can be the same level of I, or it will be one level less than more than I. If I ignore the parents, if I think j, this is I, j can be this one or j can be this one. If this is I, j can be in the same level or one level down. My neighbor, one of my neighbor will be my parent, I forget that, but even then one of my neighbors can be in the same level or one level down. So, these are the two possibilities. Okay? All of you agree? Okay. I take this picture once more. Take this small picture. Okay. Now, take this small picture. This is level 0, these two are level 1 and this two is level 2. Okay. Now, this is exhausted, I come to this node. Okay.
What are we assigning weights to the edges or the vertices?
To the nodes, to the vertices.
So what are the initial levels?
The levels of the nodes, the initial levels of the nodes is at what step BFS reaches.
No, what are these weights? What's the difference?
The weight says how many shortest path is passing through that node. Weight is how many shortest path passing through that node, while level is at what depth this node is residing. Okay. So, at what depth this node is residing, and weight is how many shortest path passing through that node. Clear? Okay. Now, see this node, this is I, j can be this and j can be this. So, what is the level of j? It can be same as I or it is one level more than I. It is one level more than I. Okay. So, if j has been assigned and j level of j equal to level of I plus 1, only that case what you do, assign weight of j becomes weight of j plus weight of I. Only if it is one level below, that means what? Another shortest path also passes through this weight. Therefore, this weight becomes now 2 plus 1 3, 1 plus 1 2. Okay. From here 1, from here 1 2. Now, it is clear, and if not, do nothing. Okay. And then x is equal to x plus 1.
So what if that node is also connected
What node? This node is
Connecting to the last leaf.
this leaf. Then this will become actually level 2. This is again the same situation as this, see. Okay. Clear? Okay. So, now after this step what we have is we have labels and weights. Okay. So, let me redraw it again. Oh, sorry. Okay. Okay. So, and what are the weights? 1, yeah, weights I am telling 1 1, 2 1, 3 1. Okay. Okay. So, now nodes have been assigned, but what is our aim? To assign weights to edges, not nodes. Nodes are not important, weights to edges. Okay. So, now assign weights to edges. So, now see what does this information means? There have been 3 shortest path coming through this node, and 2 has come from here and 1 has come from here. So, here I will assign 2/3 and here 1/3. So, if I think this as j and this as I, so assign edge weight W j W I by W j. Clear? Okay. Now, come to this node here. So, how much should be assigned? No. So, so what let us think that how many shortest path means if I take this and this into consideration, how many shortest path is coming here? Half here, half here. See, the assumption is, what is the assumption? Again see, here 3 shortest path from S to, if I think this as S and this as T, from S to T there are 3 shortest paths. That means 3 redundant paths or 2 redundant paths. And what I think that, see, from S to this T dash, how many shortest path are there? Yeah, perhaps 1 shortest path is there. And what so sum of all the shortest path for a particular source destination pair should get value 1. Sum of all shortest path for a source destination pair should get value 1. That is why what we have told that 1/3 shortest path passes through this and 2/3 shortest path passes through this. Because we are thinking that whatever may be, there will be 300, 500, we do not want, for one pair there will be 1 shortest path, for another there will be 1000 shortest path, that cannot be. We are thinking weights are same for all. So, everybody gets 1. So, this is 1/3, this is 2/3. Now, from here to here we know there are 1 redundant shortest path or 2 different shortest path. So, for there half will come here and half will come here. No, I am just thinking of this part. I have ignored this part. I am just thinking of this part, and this half is actually helping this 2/3. So, how many shortest path? Half into 2/3. This half is actually helping this 2/3. This half will actually also help this 2/3. So, here also half into 2/3. Previously, if you come to this case, what was happening? 1 and 1 more. So, 1 plus 1 2. Now, here similar thing is happening. It is basically 2/3 plus 1 more, 2/3 plus 1 more, 2/3 coming from here plus 1 more into half, because actually half is passing. Okay. So, this becomes 5 by 6 and this also becomes 5 by 6. This is 1, this becomes then, tell me, 1 plus 1 plus 1 by 3 into 1, 1 by 1. Am I clear? So, this is 7 by 3. So, this becomes 7 by 3. So, what will this be? Let us calculate this value. 5 by 6 plus 7 by 3 plus 1 into 1 by 1. How much is that? 25 by 6, and here it is 5 by 6 plus 1, which is 11 by 6. Clear? So, this part is the catch, simple catch, that you have to normalize it with the value half. Okay. So, then accordingly you get the node weights for all. Okay. Accordingly you get the node weights for all. So, again this algorithm is order m. This algorithm is order m, and then you do order m.
The aggregate calculation depends on how we are choosing
Edward?
so which node we choose as the root.
No, so you have to do it for all the nodes, no? You have to do it for all the nodes. This is one for one particular S. And then for all S's, I am just multiplying it by n. So, the complexity stays as order mn. Okay? And for sparse graph, it will be order n square. Okay. Now, what is the algorithm we are running basically? Let us come back to this original algorithm. This is the original algorithm. Calculate betweenness score for all edges. This is taking what time? Order mn. Find the edge with the highest score and remove it. This will take order m. This will take m, and remove that, recalculate. Then that this how many steps, how many times this step may go? N. This step may go n. So, total complexity is order m n square. So, that is order n cube for sparse graph. Okay? Clear? Very good. Now, we
Sir, what after one iteration, like you found weights for all the edges, then
I remove that edge. After I find the highest code, I remove it.
So highest score in what sense? Like you did it only for one source. Then you will
Yeah.
do it for all the sources.
All the source, sum it up.
Sum the weights of all the edges.
Yeah, that's why it takes order m. For each edge, for each configuration, for each edge, I am getting a score. I am summing up over of n configurations. Then I remove the highest edge. Okay. Where? Yeah, so I remove that. There will be m iterations. I am sorry. There can be m iterations. Thank you. There can be m iterations because there are m edges. Yeah, means the worst we can do is remove all the edges. So this is it is order m square n, not mn square. Order m square n. Again, that roughly becomes order n cube. Okay. It's clear? Okay, very good. So now we move around on to random betweenness. Okay. So when we go for random betweenness, what is the thing which we have to see? The transition matrix. Okay. So we try to see the transition matrix. What is the transition matrix? So given AI, given the adjacency matrix A, given the adjacency matrix A, given the adjacency matrix A, how do I get the transition matrix? So say I have 1, 0, 1, 1. Okay, I take a bad example. I don't take a symmetric example. I don't take a symmetric example, but anyway, it doesn't really matter. It doesn't really matters. Okay. So what matters is if I see the transitions, if I see the transitions what does this mean? That row I has 2 edges. Okay, row I has 2 edges. Clear? So row I or vertex I has 2 edges. So now if I have a random walk, then what will happen? Tell me. There is half chance that the walker will go this way and half chance that the walker will go this way. Okay. So from A I can perhaps build up a M. From A I can perhaps build up a M, which is basically think, or I write M where Mij is equal to Aij by Ki. Okay. So I can perhaps build up a M where Mij is Aij by Ki or Kj. It will be Kj. K is the degree. Okay. So let us think that this is Kj and I go on, I will explain. And now what we get, that we get a matrix M. So, which is basically telling that the transition at one step. Okay. Now, since we get a matrix, again we can do the jugglery that what is Mn? After n step, what will be the transition probabilities, and you can go on doing m infinity after infinite steps, what will be the asymptotic condition. Okay, what will be the asymptotic condition. So, this way you can develop whole lot of things and calculate random betweenness. I think we will explain that in details next class.